So in this video, I really just want to talk about flux and Gauss's law. We have this equation here to be our definition for flux. Now in words, what it's telling us is that the flux, phi, is equal to how much electric field is going through a certain area, A. So here we define E bar, this is our electric field. It has a magnitude and a direction. And now A, it's our area, and it has a magnitude. So in this problem here, the area is equal to d squared, but it also has a direction. And the direction it points in is the one that is normal to the plane. So this is a flat surface, the normal points all the way up here, and its magnitude in this case is just d squared. Now the angle between A and E, this is theta. In a problem like this, well, you're given theta, you're given E, you're given really everything, so you just plug everything into this equation and you get a number. Things are not always so simple, right? But I do just want to clarify a couple of things. So for instance, if I define my normal vector to be down here, this is going to be my area vector. And then if I were to say that, okay, we have an electric field coming in like this. So this is my E. The angle between E and A is, in this case, 90 degrees. Sorry, I should say 180 degrees. It's 180 degrees. And the cosine of 180 degrees is equal to -1. That means my flux here, sure, it's going to be E, the magnitude of E, times the magnitude of A. Cosine of 180 degrees is -1. That means I'm going to have a negative flux. The negative here really just refers to the difference in orientation between my electric field lines and my area vector. That's about it. You might get some weird looking surfaces like this one, where, there's not really nice area, and maybe even your electric field line, your electric field varies. So maybe here we have an electric field this way, we have an electric field this way, right? There could be a ton of them. And the idea is you use the same equation, but here, instead of just saying, well, this is our equation, you're going to have to say that my electric flux is equal to the integral E dot dA, where here we use dA because we're talking about little chunks of area. So for instance, we can look at this little piece of the surface and we can figure out where is the electric field pointing here, what's the normal vector here, and then we have to figure out how we're going to divide up our surface into tons of little chunks dA. Obviously the way I'm doing it right now is not very efficient, but usually we're going to be able to have some form of symmetry that we can exploit to have an easy to solve integral. Now I want to talk about flux in 3 dimensions now. So let's say, for instance, I have this cube, right? So I have a cube, and let's say I have an electric field coming in this direction, okay? The electric field is going to hit this surface here, and it is going to come out this surface here. If I were to draw my normal vector, so my area vector is here, this is A, and this is A, and this is E. So the angle between the electric field lines and the area vector here is 180 degrees. The angle here, if I draw my field lines, the angle between my area vector and my electric field lines is going to be 0 degrees. So here, when I have cosine of 180 degrees, this is going to give me a negative flux. And this time, we are going to get cosine of 0, which is +1, so this flux is going to be positive. Now, if I have the same amount of electric field lines coming in, and this area here is the same as this area here, this negative flux is going to be the same in magnitude of this flux, just in opposite directions. So here I have a certain amount of flux coming in. We can imagine like I have a positive flux here, and we have negative flux here. Add them up together, the flux is 0. So explicitly, I say F net is equal to, here we're going to have the flux on the left wall plus the flux on the right wall, and that's going to be equal to 0. So the idea is that unless there's some source of electric field lines inside of my volume, I'm not going to have a flux. And that is, in essence, what Gauss's law is. So if I were to write out Gauss's law, it's going to be as follows. So the electric flux is equal to the surface integral of E dot dA is equal to Q in over epsilon naught. So I only have a flux if there is some charge inside my volume creating those electric field lines. For instance, if I have a sphere like this and I have some positive charge inside the sphere, it's going to create electric field lines pointing radially outwards. Now I'm also going to have my dAs here pointing radially outwards in the same direction as my electric field lines. They're in the same direction, so cosine of 0 is equal to 1. So I'm going to have a positive flux. And the positive flux is going to be proportional to how much charge I have in. Just think about it like this. I'm not going to have that many field lines coming out. If I have a very large amount of charge here, my field lines are going to get pretty dense because my electric field is just going to be that much stronger. We see that they are proportional. Now, if you remember from the earlier parts of the chapter, we were dealing with similar things, right? So for instance, we had the disk. It had a certain amount of charge. Well, it had a charge density sigma on it. And we were trying to figure out, well, what is the electric field way down here? And to solve that, we had to actually work pretty hard, where we had to divide it up into concentric circles and figure out, well, what's the electric field due to each of these little circles, or these rings, and add them up and all of that. That was a little bit difficult. Here, what we're saying is that we are able to figure out what the electric field is, say for instance, way down here, just using this equation instead. Now, of course, there's a little caveat, which is that this is not always an easy integral to solve. But what we're going to see in the coming problems is that there are certain cases in which this becomes very, very easy to solve, and then from Q in, we'll easily be able to solve for the electric field. From an electric field, we'll easily be able to solve for Q in. So hopefully that's going to make sense in the coming videos. I should note, however, that we can, of course, solve a problem like this that deals with this sphere using our methods from earlier, in which we had rho times dv, and we had to take the integral and add up all the little components of dq. We can do it that way, but what we're going to see, especially for spheres, is that using Gauss's law is definitely going to be the way to go in terms of just how fast we're going to be able to solve the problems.